Hello, everyone. Welcome to another meetup session. This week we have a very exciting topic on autonomous driving, and we all heard about this big buzz about self-driving vehicles and how big companies are trying to use deep learning to try and push the limits on this field. And for that reason, we invited some great speakers to speak and tell us a bit about this area. I'm going to welcome Christian and Ana. They're going to be our speakers for today. And before giving them the word, I'm just going to do a brief introduction. As usual, you can expect a session with the format of more or less 45 minutes for the talk and then 15 minutes for the question answering. And feel free to post all your questions in the chat. We will address them or try to address them all in the end. So going to the biography of the speakers, Ana Ferreira is a senior software engineer at Woven Planet, level 5, where she currently works as technical lead for the planning team, and she also has worked with the predictions team. And Ana comes with a lot of years of experience working on this problem involving driving vehicles and robots and, you know, all this kind of control area. And she has also worked in Apple in the Autonomous Systems Special Projects Group, whereas Christian is a senior ML engineer at Woven Planet as well in the research team in London, UK, and he has previously worked in Hewlett-Packard Research and Development Labs, and he counts with more than 11 years of experience so far. And their biography is way too big for me to go over it. So if you want to know more about them, check their LinkedIn profiles or the biographies we have available on the meetup. So without further ado, I'm gonna pass the word to them. And yeah, welcome and thank you so much for accepting our invitation. Okay.
Yeah. Hi. Thank you, Katarina. Thanks a lot for the invitation. It was a pleasure to be here as well. I participated in some meetings at the past, so I'm very happy to be here. So yeah, my name is Christian, and as Katarina said, I'm working on Woven Planet, a senior machine learning engineer on the research team here in London. And together with me as well, there's Ana. Ana, I don't know if you want to introduce yourself as well.
Hello, I'm Ana. I'm a senior software engineer. I work in the Palo Alto office at Woven Planet, but I collaborate with Christian almost every day.
Cool, thank you. So let me start the presentation. So basically, this presentation will be, like a overview of, like how we took our self-driving system, autonomous driving system stack to go from an expert system to a completely data-driven system, right? So we will be talking about the challenges, what was the lessons that we learned during this whole work, and also at the end we will show as well some, like examples and some videos of our car deployed in San Francisco as well. So the agenda for today will be mainly to talk, like a very short introduction and starting also with, like some basics about imitation learning. Then we'll go through, like a data-driven approach that we use for driving. We'll talk about our architecture, data sets, and then results and deployment and what we are working on and investing time right now on the next steps for the self-driving system that we have. So yeah, but before I start, I would just give like a brief overview and the story about like Woven Planet. So basically, Woven Planet is a subsidiary of Toyota, and with the main mission of building autonomous drive systems that are safe and reliable to transport people. Right. So we have today more than 2,000 people and 3 global offices: one in London, UK, one in Tokyo, and another one in Palo Alto in US, which is where Ana belongs to as well. And this is a little, like a timeline of how all this happened, right? So everything started in 2017 with Lyft deciding to starting a autonomous driving division. So Lyft started what was called the Level 5, which is a division for autonomous driving inside of Lyft. This started 2017. In 2018, we started the public, like testing on public roads, and then 2020 we already had our 4th generation of autonomous vehicles as well. And 2021 we have been acquired then by Woven Planet, which is the subsidiary of Toyota Motor Company. But just before that acquisition, some months before that acquisition, we started deploying also our system in San Francisco. And that's where the focus of this talk will be, about those recent developments that we had on just before the acquisition and until this day. So an introduction on how the traditional stack for self-driving system works, right? You have what is usually called the AV, autonomous vehicle, or also called the Eagle, right? The first thing that you have is that you have plenty of sensors, right? You can have LiDARs, you can have radar, you can have all sorts of cameras, right? And this gives you a sensor, a sensing around the environment that the Eagle is driving by, right? But you don't want to work in this raw data space, right? That's hopeless. That's why you have usually another pipeline, another stack after that is called perception, right? That converts all this raw sensoring data to a more understandable and semantic data that you can work on top of it, right? So that basically means detecting where all agents are in the scene, detecting where the car is in the scene as well, right? And then you usually have also one step of prediction, right? Which is very similar to how humans drive today. For instance, when you are driving, you are all the time trying to anticipate where other vehicles and other agents might be in near future, right? So that's what's usually called prediction as well. We are trying to anticipate the future and to be able to later plan on top of this future according to some goals that we have. We want to define what will be the plan, what will be the trajectory that Eagle will follow to achieve those goals, right? And after that, then we have control, which is basically the execution of this planning, of this motion planning that happened before, right? So those are usually the main, of course that you can have, all sorts of, variability in the way that this works. You can have end-to-end systems, you can have mid-to-mid systems, you have many different flavors of that, right? So here we show a more pictorial description of that shows every step of taking. And usually nowadays is that what happens is that the amount of machine learning and the data-driven systems that we have are usually on perception and prediction and not much on the planning side of it. And our vision is that it won't be possible to scale out if we don't go through fully data-driven systems. So that's why we are driving as well towards having a fully data-driven planning as well on top of those stack. So this will be there's a lot of things going on machine learning, deep learning for vision as well, but the main focus of this talk will be on the part that we work on, which is on the planning side. So basically just this is to stress a little the difference on the what are usually done in planning with rule-based or expert systems, and what is the difference with data-driven systems. On rule-based, you have to handcraft a lot of rules, right? To decide what trajectory we'll be following, and that is very difficult to scale, as you can imagine, right? The variability of experience that you can have on the real world are very difficult to capture by handcrafted rules, right? Although we have some advantage of doing that, which is makes it more interpretable and also easier to embed, for instance, concepts such as causality, right? On the other hand, we have data-driven system that has shown, to absorb and learn with a lot of data and to be able to scale easily. Not that easily, you need computing power as well and data, of course. But, it has proven that, nowadays you can get big models with big data sets, and you can have systems that achieve major breakthroughs, right? One benefit of that is that also easy to adapt, but there are some, of course, downsides of it that makes it less interpretable, and we have also other challenges with data as well, right? So let me go to the next slide here. So I will talk now about introduction about imitation learning, right? So usually imitation learning is this decision process, right? The sequential decision process is usually formalized in a framework that's called an MDP, which is Markov decision process, right? This is composed by a tuple of 4 different components, right? The first one is the state space, right? where you have like states that are sampled from this all potential states that you can reach, right? This means like all configurations that you can have on a scene, for example. And you have also the action space, which is like the space of actions that you can take at a certain point in time, right? That are discrete as well. You also have transition dynamics, right? So given, like a current state and the action that you took, what will be the probability distribution on top of that will lead to next state, right? And you can also have, the cost or can be sometimes called a reward that tells you, like given this state and action, what is, like the cost of this action in this state, right? So basically this can be seen as this graph here, right? Where you have, let's say that you are on a current state, you have then an observation, because what can happen is that you don't have fully observability about the state, right? There might be some things about the state that you don't know. So what you observe sometimes is not the full state, right? And then on top of that, you take actions that can give you rewards or costs, right? And then will lead you to another new state, and that repeats on and on, right? So this is basically a very short introduction to what is called MDP decision process, right? The goal here is to find a policy, right? So what a policy is basically a decision on top of a state that tells you what will be the action that you need to take at that state, right? But we don't want a random action, right? We want to minimize some, some objective, right? And the objective that we have here that we want to minimize is this cumulative expectation, right? On this cumulative cost over time, right? Over some time steps. And that's what we want to minimize when sampling from this policy that you have, right? So states and actions are induced from this policy, right? The big problem is that, well, actually we don't know in self-driving systems, we don't know what actually is the cost, right? It's very difficult to tell what humans are using as a cost to take decisions, right? So that's a very complex problem. However, you can get away from knowing that by going through what is called imitation learning, right? By imitating humans or collections of data taken from humans or other expert systems, right? So imagine that you have a data set that is composed of pairs of state and actions, right? And then once you have that, you can pose that as, like using the most traditionally used and most, successful way of training models, which is through empirical risk minimization. And you can say that, well, I want to minimize, my policy, decisions from my policy to imitate the actions from the humans, right? And you can see here as well that, when you see this formulation, you can start to see as well that there are many also, choices that you need to do. Like, for instance, what will be a better, a better cost, a better loss to use to imitate humans, right? So some things are not that clear by looking just at this formulation, right? So this approach is mainly, the approach that is being used nowadays for many places, right? And this dates back to 2009 paper from Alvin, which was the first one to use neural networks on self-driving cars, right? And the problems is very interesting because the problems that was, limitations that were mentioned in 2009 on this paper, some problems continue until this day. So it's a very challenging field, of course. But that's exactly what we will be talking here, and what were solutions to solve those problems that are there for such a long time now. So just for you to understand a little about what are the usual issues with imitation learning, one of the main limitations is what's called compounding errors, right? So imagine that you have your AV, your policy that's controlling, and then you take decisions based on the policy that you have, right? So you have a parameterized distribution here that tells you, given that state, what will be the action, where your ego should move, right? And then what happens in practice is that you train those systems, and when you deploy, you see that they start to diverge, right? They start to diverge, and once they diverge, it becomes very difficult to recover from that, and they follow trajectories that are not expected and not seen during training as well. So the way that you can imagine that why this happens is that you can imagine this state action manifold, right? Where you are sampling from this space by collecting data, right? So when you collect data, you can imagine that you're collecting data with humans driving cars, right? And you have a portion of this manifold that you explore, right? This state and action space, right? And then you can imagine like each point of those, each point is shown here is one example, right? It's some scenarios, some problems that you might see on the traffic, right? But then when you start to diverge, you start to go into regions of this manifold that can be seen as out of distribution, right, from the training data that you collected. Because if you collect data on this region of manifold and you start, and the model starts to make tiny errors, it will start to drift a lot. But by doing a lot of tiny errors, you start to compound, and then you reach this space of this manifold where you do not know how to recover, simply because it is out of distribution. So this is traditional problem in machine learning, not only imitation learning, right? It's generalization for data that you didn't saw before, right? And what is happening here, right? So what is happening is that, well, when you collect data, your state distribution and your action distribution comes from the police induced by the human, right? You collect human data, you have a police from the human that collects this state distribution and action distribution. But when you deploy it, the state distribution is different than the one that you used to train, because what happens is that you are taking decisions using the policy that you trained it, and this policy that you trained it might make tiny errors and compound during time. So this is the reason why it happens. You are training on one distribution and then doing inference, and during inference you are reaching to different distributions that are not on equilibrium with the ones that you had before, right? So you have this big mismatch problem on imitation learning, right? We will talk more about that later and what was the solution to it. And I will leave now to Ana to talk a little about, like the data-driven approach that we take for planning.
Thank you, Christian. Yeah, so we will talk in the next sections about like how we employ this knowledge to build our data-driven planner. And so the way we tackle this data-driven approach for autonomous driving. So let's start a bit high level first. So here you see these are the two pillars in which we build our data-driven approach. First, we need to be able to massive harvesting of real-world behavior data. So we need a lot of data to feed our data-hungry systems. On the other hand, the second pillar is to build a self-driving system that can actually improve with data. And if you recall Christian's first part, one of the newer, bigger components that require more novel approaches are going to be here the data-driven planner and the simulator, because those are the ones where we're looking at replacing our rule-based systems. So let's talk a little bit first about the data. So one of the big trade-offs when we consider data that we need to address is this like data quantity versus perception accuracy. When you think about the main typical self-driving car that you might see on the news or in like blog posts, you're looking at the car on the left, which is this autonomous vehicle with very high definition sensors, such as LiDAR, possibly an array of multiple high resolution cameras, and even some radar sensors. So unfortunately, this is quite costly and computationally intensive. So even though you get quite high perception accuracy, you will find that your quantity of data is going to be much lower. On the other hand, you have the cars on your right side, and you can think of your own car, which nowadays can already come with a few commodity sensors, perhaps a few cameras of lower resolution, and some radar sensors, typically shorter range. But these are fairly cheap, which is why they are becoming widespread. So you can think of like we have like a big fleet of these data, and for us, being part of as a subsidiary of Toyota, we can actually have the option to have access to some huge fleet data that we get from like a lot of Toyota cars. So of course, on this side, it comes at the other trade-off, which is we have a lot of data, but the perception accuracy is significantly lower. So there are a few challenges that come down with this, and we have to figure out how do we actually can leverage this data to feed a data-first self-driving stack. So next slide. So one key challenge for our team is, how can we use this cheaper, lower fidelity data? One of the first questions that the team answered was whether we could rely on learning from low quality data and whether these transfers to a high definition sensor autonomous vehicle, which is the one we use to deploy our planner. So a few questions that we have is, what is the quantity of low cost data that we need to make up for the loss in quality? And then other question is, can we transfer learnings between these two different sensor modalities? Can we train on a mixture of these two different data sources and see if our planner generalizes well? And so next slide. This is what our team did. So what we did first is we grabbed this high definition AV data set that we had that is very high quality. And we actually degraded into some simulated lower quality data. We use this lower quality data to train our ML model. And then finally, we fine-tuned this model with a little bit of the high definition quality data. And then we evaluated. So what the team actually showed, as you can see in the plot, is that, so on the very left, you have the planner trained with only the high quality data. And it actually, if you go into the middle plot, we train it on a much larger, much bigger volume of data, of lower quality data. But we can see that we actually can get fairly similar performance. And then even further, on the right side, you can see that if we combine the two data sources together, so large, and in this case, large amounts of the lower quality data with a little bit of high quality data, we can get even better performance. So this is what the team showed, and it actually in a paper in ICRA 2021, is that we can actually use larger amounts of data, of lower quality data, to train an AV. And then since then, we have also showed that we can get similar results if we use some real fleet data of lower quality using these commodity sensors. So these are really good news for us because it really opens the door to like using this crowdsourced data collection, data that is cheap and high volume, that we can actually use to train our autonomous vehicles. And so this is one of the big pillars for our approach. So we talked a little bit about data, and so let's switch gears towards the other pillar, which is how do we actually build our system? How do we build our ML planner? So let's dive to the next slide. So this is how the ML planner looks like. So first, very high level view. And as Christian mentioned earlier on, so for the planner, what do we have as inputs? We will have the localization of our car, which we typically call ego. That's going to be our own car that we are planning for. We have these perception agents that can be vehicles, bicyclists, pedestrians. We have also from perception the traffic light status. And we also have this HD map, a high definition map that gives us some semantic information about the lanes on the road, where the lanes might take us, can we turn on that lane, and even like which traffic light is associated to which lane. And so we have all that information that is fed to the planner. And then the goal of the ML planner is to generate a planned trajectory. So like that will be the trajectory of our car, which again, we call ego. And we plan a trajectory for some horizon, typically about 5 seconds of where we want the car to go. And this, if we deploy on the road, is fed to the controls, the car controls, or it can also be fed to simulation if we're doing like large scale evaluation. So a brief overview of our ML planner. So now let's go into what that block of the ML planner actually looks like. Our approach for the ML planner is a graph neural network that has 3 big-ish components that we highlight here. So the first one is what we call this local subgraph. And then what it does is it computes the embeddings of each of these elements in the scene independently. So we have the ego, we have the agents, and we have the different map elements. And they all get encoded independently into some embedding. Then we have the global graph that what it does is to reason about the interaction between each of these agents and the map elements and ego and how they might affect ego behavior. And so that will reason about give information about what that will affect ego behavior in the future. And so that information gets passed into the last component, which is the decoder. And the decoder basically generates that trajectory that I mentioned before, which is just a trajectory of some horizon from timestamp 1 to 3 through t in the future, which can be about 5 seconds. So let's go a little bit more in depth into some of the nitty-gritties of our system. So let's look at the input first. So our input is a vectorized input. So if you see there, we look at our ego, which is the red car. We map it into some sort of a polygon where we might represent centers, we might represent corners of the polygon, and some of its history as well. Then you can see 2 and 3 are going to be the other agents on the road. And we will also encode some vectorized features about these agents. And then finally, we also vectorize, let's say, the different lanes, the lane geometries on the road. We might vectorize, as you see, 5 there, which are actually the crosswalks that occur, that we can find on the road as well, where pedestrians might be walking. And then other lane aspects or even, let's say, speed bumps that we find on the road. And so all of that gets vectorized and is fed into this local graph. On the local graph, we typically follow this point net architecture. It allows us to handle these vectorized inputs of flexible size. And one neat thing that we use is that positional encoding there, that it allows us to encode some of the history, in our case, for instance, for ego and agents, where we have history, we can use the positional encoding for that, for these temporal elements. So then let's look a little bit more into the global graph. So that is a transformer module. It's fairly standard in the industry and has recently shown very good performance, as you see in multiple papers. In our case, it learns the weights that generate this attention between the different elements of the scene and our ego car. So you see there, we feed as query to this transformer the ego embedding, because the intuition here is that ego is the query, because that is what we want the network to learn, some embedding that contains the information about the ego future trajectory. An interesting detail about this transformer you might see there is that type embedding. That is an embedding we use to represent certain types of the different elements in the scene we see. So for instance, a crosswalk can be embedded there, but also, for instance, the traffic light, like a lane that has a green traffic light or a red traffic light, might also be embedded as a different type. And then finally, like the agents even, like if you have a bicyclist or a truck or a pedestrian, that can also be distinguished to the network as a different type embedding. So then finally, let's look at the last component there, the kinematic decoder, or the decoder. In our case, it's a kinematic decoder. So what happens there? Because we feed our trajectory into a controller, we need our trajectories to be smooth. And it's not always a guarantee that we're going to be able to generate a smooth trajectory out of a neural network. So one approach we followed is that instead of generating the trajectory directly, we actually generate these higher order terms that you see there represented as K and J. And these are actually curvature and jerk over time. And so that's what we actually predict. And then what we use is a kinematic model of a simple, if you know controls, a simple unicycle model. And then we integrate these higher order terms over time, and we can then generate an ego trajectory that is smooth. So yeah, hopefully this gives you a little bit of idea of like the different components that we have in our network. So next slide. So let's now come up again and talk a little bit about how we train our network. So so in our paper Safety Net, we use about roughly 300 hours of driving logs that we have from the road. We train our model on 64 GPUs, and we are able to train it on the cloud, and it takes about 5 hours in this case. And the way we train it, as Christian pointed out, is in this case behavior cloning. So what we do is we picked this logged trajectory of what actually happened on the road, and we compare it to the ML output. So then our loss there is going to be we want to minimize this distance. So we're looking at minimizing this distance and hoping that the network is learning to like generate an ML output that is as close as possible to the log trajectory. So next slide. So one key property that we see is that so when we're looking at interventions per 1,000 miles, so in our case, lower is better, less interventions, is that indeed if we feed more data into our model, we actually get better performance. So this is a key property for our pillar of building a self-driving autonomy, data-driven autonomous stack, which is our ML planner can actually improve with more data. But is it this easy? And the answer is no. Next, we'll go through a few challenges and approaches that we have gone through to improve our data-driven system. So a first one is closed-loop performance, which Christian already talked about, but we'll go through an actual example. So maybe for some of you that are working more on the perception realm and vision, this usually you don't find this challenge as much, which is in planning, you can't really just plan once. So in planning, you need to have this good behavior in a sequential manner. So like you plan, you will put your car in the place you planned, and then you have to plan again. And you have to always be able to generate a good plan, even though, as Christian mentioned earlier, you might end up drifting away from the data that you've seen when you were training. So here, this is one nice example we see here in this GIF. So our car is supposed to be doing a left turn. And in blue, you see what the logged ego vehicle did on the road. But then in orange is our ML planner. And at the beginning of the scene, our turn actually looks really good. Like it's following the lane, is doing well, but then eventually it starts drifting away. And it drifts away enough that eventually the network does not know what to do. So next slide. So here's what happens. So when you plan only once, you start with your ego trajectory, you plan the trajectory. There is a little bit of error in it, but that's okay. You'll be like, okay, well, our ML planner is never going to be perfect. So there's a little bit of error there. If you keep your car in the same place where it was originally on the log, you create another plan, and that's going to be fine. It has a little bit of error. The problem is when you go to the second plot there, which is planning sequentially. So if we have a little bit of error, now that we plan sequentially, we put our car in the next step, and then it's going to create another plan trajectory. It's going to have a little bit more error, and these errors are going to sum up and compound into a much bigger error. And eventually, the car is going to be in a situation that it doesn't know what to do. So are there ways to mitigate this? The answer is yes. We've explored a few approaches, and Christian will tell you now about one of them.
Yes, thank you, Ana. So continuing on top of what Anna just discussed, I think it's very important to reiterate that and reinforce what is the biggest difference, between what we call open loop and closed loop, right? When you do evaluation, or when you usually people train those behavior cloning models, they are training in open loop. So what happens is that, well, you have the ego, right? You have the EV, and then your model does a prediction, and then you compare this error with the ground truth here, right? And then on the next step, you reset the ego position to the ground truth, and then you do again this loop, right? You keep doing this open loop prediction, but the problem is that you are resetting it. You are not taking it sequentially, like Anna said, right? You are not planning sequentially. But when you deploy that, or when you do evaluation on a closed loop manner, what happens is that you have the ego, you do a prediction, and then the ego moves, right? In reality, you do a prediction, and then that goes to controls, and then you are actually taking an action in environment of you moving the ego, right? So that's, as you can see, it causes a very big mismatch between how the model is being trained and how the model actually performs during inference time, right? So this is one thing to keep always this picture clear in mind, because this is a very fundamental difference that can cause a lot of issues in those models. So how do we work it towards trying to overcome that issue is by doing closed loop training as well, right? And this is described on the paper below. Later you can check more about it. But basically we have this human driven training trajectory, right, that the ego is following. And what we do in closed loop is that instead of following, resetting the ego every time, what we do is that we have a simulator where we do a unroll trajectory, right? So this is very similar to how we do in reinforcement learning as well. We have those rollouts, right? So we have a rollout, which is basically taking the policy on an environment, right, on initial state, and then you use the policy to unroll it, this trajectory, by taking actions sequentially using your trained policy, right? So we do this during training, right? So we do this at every step of training. We do those rollouts, and then what we look then here is the error that the policy did, and you can see that this error here is very different than the error that we saw before. The error that we saw before was always like one step or a few steps ahead, and this is the error after the policy interacting with the environment, right? After the policy is moving the ego in the environment and taking control of it, right? So, however, if you do that just naively, you can end up introducing biases as well. So the difference on our approach here is that what we do is that we have this first initial step here, where we sample from the trajectory, we sample initial trajectory, initial state from the policy, and we don't use that for learning. And why is that? This is because in the beginning, you are starting from a state of the ground truth. So what we do is that we use the policy to take a few steps, and then this will naturally perturb the state, so it will be different than the ground truth state, and we use that as a warm-up, right? Trajectory part of that, which can be considered also as roll-in. And then later you have the rollout here, which is where we use this data to do the policy update, right? So we do the back propagation through this simulation that is differentiable, and what we do here is then we use this part or those errors to learn and change this policy using this part of trajectory, right? This has some very good benefits, because it is bringing inference time, the sequential decision, the sequential nature of the problem during inference time. You're bringing that to training as well, and this reduces a lot of discomfort breaks, that's called DBs here, and also improves in passiveness, right? And one good thing is that if you have a simulator that is differentiable, you can backpropagate through time, through all the steps that you took during the rollout, right? So that's very interesting. However, of course, as you can imagine, it's slower to train and scale as well. So that's one disadvantage of it. And also another disadvantage is that, well, agents around the ego and everything that's around the ego is also logged, is log replayed, right? So we are replaying the agents. We don't have, in simulation, we are not actually controlling the agents. We replay what we saw before. So they are still logged, and we are not really interacting or exploring, right? Because if the, if the ego takes a different decision, the agents are not going to respond for that accordingly because they are log replayed, right? And you are still doing imitation, so you're not exploring on that scenario. So there's some benefits and some downsides of doing that. That is important to mention as well. So those here are some qualitative results as well of this approach. You can see here in the beginning, for instance, that you can see that the ego here is depicted as a red box here, the car, and the other blue are all other agents on the traffic, and the colors here that are green or red is if the traffic light is open or is red or green, right? So you can see that even on a very difficult scenarios that are very dense in traffic, the ego was able to drive quite well, and it's able to come to stop at every time and avoid collisions and having a lot of very nice turns and follow trajectories very well, right? So this is one very big achievement for this model, right? I would like to talk briefly about another issue that you can have that's not only a problem of closed loop training or open loop training. It's a more general problem that we have in machine learning that also plagues imitation learning as well, which is about causal stability, right? For instance, if we look at this log on the left here in the figure, we can see that we have the ego there and there's a car behind it. That they are stopped on an intersection, right? So let me play again here. You can see that the ego is able to start, and they start to move, and the car follows the trajectory that was on the ground to capture before, right? However, if you just remove artificially that car behind it, you see that your policy has a very different behavior, like you see here on the right. You can see that it gets stuck there. If you remove the car behind it, the ego does not move at all. The policy just stays still there. So why does this happen, right? It happens because the model learned to capture spurious correlation instead of causal relations, right? So the problem here is that the policy is relying on the car behind it starts moving for it to start moving as well. Because of course, during training, you have a lot of those correlations, right? It might be the case that cars behind it saw that traffic light was green, and then they started to move before you, before the ground truth, and then the policy is picking up this information to take actions instead of picking up the correct relationship, which is the traffic light, right? Or being without any traffic during the intersection, right? So if you think about it, the model is doing the right thing, but it's doing for the wrong reasons. So if you don't remove those agents, if you don't come up with the diverse scenarios, you won't be able to see that before you deploy on the real world. So it can be very costly to detect that only when you deploy your car, right? So you need to have means to uncover that during virtual simulation. And you also have to to have means to overcome that. We won't be digging further into this, but just a hint of that is that you need to think what will be the cause of those issues, right? And what will happen if the model is trained with data that breaks this relationship, and just having this data that breaks this spurious relationship is enough to make the model learn that correct behavior, right? So those are some questions that we like to leave here, and we will probably be publishing a paper about it by the mid this year, end of the year. So one way to uncover that is by going through simulation, right? The problem during virtual evaluation is that, well, you need to have you replay the log trajectories from other agents when you recorded data on the street, right? So the problem with that is that agents are not reactive, right? For instance, this example, if the self-driving vehicle just stays still, this stops, what will happen is that the agents will just go over it as if nothing happens because they are not reactive. They are just log replayed, right? So what you can do is that you can use simulation to detect failure modes and also detect this causal instability of the models. But you need to go beyond just using log replay data, right? So one way to do that is by going to rule-based simulation, right? You can adopt human knowledge and create some set of rules for driving agents during simulation and use that to evaluate, right? However, this has the same problems of of the prompt that we mentioned before of an expert system. You have to hard code a lot of rules there, and you have to be very careful in doing that, right? So another approach that we can use the same principles that we use to train the ego to train other agents, right? So we can use the same architecture that Anna showed before to learn how, like agents around the ego behaves as well, right? So this is exactly what we did on this paper that's called Signet, which is basically a simulator that is data-driven, right? So we control every agent in the scene that is on the radius of the ego, and we decide actions on that by using this policy, this reactive policy that we learned from the data by watching other agents drive as well, right? So that's quite interesting, and that was one of the ways of uncovering the problems that I mentioned before about causality, because during simulation you will be simulating then a variety of scenes that you didn't saw on the street, right? You will be doing virtual validation and will be able to uncover a lot of different scenarios and see a lot of failure modes and also causal issues that will help you a lot into identifying and anticipating issues before going to the real world, right? I will briefly talk now about our data sets, right? Not only we open source code for the, like the papers that we mentioned, but we also open source very big data sets, right? The first one is the perception data set. We have more than 30K annotated LiDAR scans with 1.3 million annotated images as well, and also semantic map for the area of driving of this data set. So if you are interested in playing with perception data set, just go to this link here later. We will share the slides later as well if you are interested. And we also have a data set that's more for prediction planning, where we have 1,000 hours of traffic logs. So it's a lot of driving that you can play with and train models. And we also released 15K semantic map annotations as well, and also together with very high resolution aerial map of those regions as well. So it's a very interesting data set where you can play a lot of that and learn a lot by inspecting and understanding this data set and training policies on top of it. So I will leave now with Anna that will talk about, like a deployment and show some results in some very interesting videos of deployment for car in the real world, right?
Next slide. So yeah, we acknowledge that our ML planner is not perfect. And one of the questions is, how do we actually deploy the ML model in a safe manner, especially for such a safety critical system? And so we worked with the team to create what we call the hybrid planner. So as you see there, we have the ML planner architecture, as we saw, that generates an ML plan trajectory. And then what we have is this expert fallback layer trajectory. What it does is checks the trajectory, its feasibility, like it checks for comfort, safety, legality. And if all of that passes, that gets fed to the controllers and to the simulator. If for some reason that doesn't, some check fails, what we have is a very simplified expert system that will still generate feasible trajectory candidates, but it will still try to pick the trajectory candidate that is the closest to the ML trajectory, and then that's the one that gets passed to the system. And so with this, we are able to create a safe learned planning. So next slide. So we have a few simulated results on like how the hybrid planner can improve and allow us to trust that we have a safe planner. I will not go through the values for the sake of time, but you can find them in the paper and a discussion about it. And then the other note is one thing we didn't talk in this talk is like challenges about deploying these models in a real card hardware, so potentially different GPUs models, different compute, as well as latency considerations. But all of those challenges are there. So yeah, I think next we can show our video about our hybrid machine learned planner. So next slide, Christian. In the dense streets of downtown San Francisco. Is it playing? Yeah. So what you'll see here, these are scenes that our plan has learned the behaviors entirely from data. So typically, like a lot of cars on the road, as you will see here. So in the first case that we'll see here is that it's a cut in, a car coming from the adjacent lane, and our planner has to learn to comfortably slow down and allow this vehicle to merge. So next, we'll also see this car almost perpendicular to us merging into our lane, and then our car ego, our ML planner, has to slow down for it. And then in the third example is a little harder one. We have the cars on the right that are trying to merge into our lane. We kind of have to let them go, but at the same time, we also need to be able to progress in our lane and continue through traffic. So this was a nice negotiation. Here, we see nudging, where our car has to go around another vehicle a bit in our lane. We also have these parklets for restaurants in San Francisco, and our car has to nudge for those big parklets. And finally, here a situation of a parked truck with pedestrians and then also a red traffic light. And then this final example where our car learned to accelerate a bit to make it through a yellow traffic light. So I think what's interesting here is that if you ever worked on like a rule-based planner, you might have had the experience that there's so many parameters and thresholds to encode. For instance, if you have to do nudging or like handle traffic light transitions. And in our case, really like our planner has learned these behaviors. They emerged from the data that we use for training it. So this is very exciting to us, and we deployed it in San Francisco. So yeah, Christian, what's next?
Yeah, that's very exciting. Thanks, Anna. So what comes next, right? So what we are doing next. So I will go very briefly because in terms of time, I think we are almost over time already. So what we are continuing to do is closing this gap of sequential decision making, right? We want to bring more of what inference looks like to the training, right? To make like those distributions met and make like this sequential decision be as similar as possible to the reality, right? The other thing that we are working on is learning to search, right? How we can, take advantage of searching during inference and also during training, right? In those trajectories. The other, of course, is something that we mentioned already, is about the scaling data, right? We are, imagine Toyota is the largest car manufacturer in the world. So you can imagine, the scale of data that we will have access now, right? And also leveraging low-cost sensor data as in scale as well, right? So that is another big challenge that we are working on, but we already saw that that is proven to show a very, very good results by adding a lot of data with more commodity sensors, right? So yeah, thanks a lot. Just one last comment is that we are hiring, of course. We have offices in Palo Alto. We also have offices in London and Tokyo, and looking for research engineers, for research science, deep learning engineers, and software engineers as well. And here it's the career website and also the Twitter that you can take a look and follow as well to see more about the positions that we have. And yes, please feel free to apply there or reach us to, if you have any questions as well. So I think that now we go to the questions. Yeah.
Hi, thank you so much. Let's start with a few round of questions after this great presentation. Thank you again, guys. So let's start with this question from Thomas De Silva Paulo. He asked, first he congratulated, he said great intro, and he was wondering if the ideas from sim to real techniques, like for example, domain randomization, can be applied to reduce that gap somehow.
Yeah, that's a good question. I will start first, and Anna, please complement if you want. But basically, yeah, one thing that we are already doing that is going towards that is that we're not using like domain randomization, but for instance, when we train CLT, we do enrolls on a simulator, right? So this is we are already using a simulator to improve performance on the real world deployment, right? So this is one thing. But you can also have, right, of course, domain randomization, and this is usually the case when you have like an end-to-end approach where you are going directly from the raw pixel space, raw sensor space to decisions, right? So, and those policies, it is very important if you want to simulate, if you simulate, right, for instance, LiDAR, radar, or images, you need to adopt a sim to real transfer technique. Otherwise, you will have like the sim reality gap problems, right? And this is very common in this area. Although I think that we are still not quite there in terms of like improving performance with those techniques, because simulating on the sensor space is very, very difficult, and although domain randomization shows some, like a performance benefits, it, like doing this adaptation can be very tricky in the real world. So yeah, I think that it's much easier to do simulation on the space where we do, which is on the after perception stack, right, where you are on the semantic space. It's much easier to simulate that than simulating on the raw sensor space. Yeah. Anna, please feel free to chime in as well if you want.
Good. CLT means closed loop training.
Okay, cool. Thank you so much. Maybe you can ask a few other questions. Ines Pelu asked what kind of features you use from the agents and whether it's information, if it's the information perceived by them about ego.
Okay.
So I guess you mentioned that you had 3 types of inputs: the ego, some information about the agents, and the roadmap. So I think that Ines is asking what exactly you are using as the agents.
Yeah, I think the first part of the question, yes, about the different features we use, I think you can think of, anything around like their state, that perception gives us, their state, center, position, the corners, so kind of like bounding box size, the type of agent. We could also explore further. Sometimes a perception stack might give you some variance information and some uncertainty about like some of these predicted states. So that's also something we can use. The second part of the question, I don't know if that means information perceived by them, meaning the other agents, about the ego. Maybe this is luring at are the other agents being affected by ego? And I think this is a little bit what Christian had mentioned in closed loop training, which is right now we only use these logged agents. So if our ego does something different in closed loop training, and as we simulate this closed loop training, there is no reaction from the other agents. However, as we are developing our Signet approach, we could start considering making these agents a bit more reactive and taking into consideration the ego behavior. Hopefully that answers the 2 questions.
I think so. Thank you. Let's have another 2 more questions, perhaps. We have here NL saying we hear a lot of that ML models need good data and not just lots of data, so data quality. Your results seem to show otherwise. Did you use the low quality data as is to train the planner, or was it significantly different?
Yeah, I think that this, like it depends on what is the, like a meaning of quality, right? For instance, you can have a perception stack, right? That is not that precise, like in detecting the bounding box or detecting localization, but can still be good enough, like for us to drive, right? And it's the same with humans, right? If you think about, you don't know exactly what other cars are around you. You don't have a LiDAR, right? So it's a very interesting problem, and I feel that the level of precision that we need to be able to drive is much lower than what we actually have by using LiDARs and radars and all those kind of sensors, right? So it seems that, there's no need for that precision to be there for a planner to be able to drive, right? Now in terms of, using lower quality, what we are saying by lower quality is mainly, a little, worse perception quality, a little worse, because of the sensor that we are using. But on the other hand, imagine, the scale of data that you can go by not having, expensive hardware to be able to collect it, right? So what we are saying is that, well, going to that direction is very promising, because that, that show it already, we show that, it can improve results a lot. And also mixing results of a different sensor with those sensors can also help. So there's like a, like you can take leverage of this statistical strength from other, kinds of data that are higher quality and transfer to the lower quality sensors as well. I don't know, Anna, if you want to talk briefly about that as well.
Yeah, I'm fairly open-ended, but yes, I think some of it is, with these larger data sets, we have like a lot more diverse behaviors, and we see that that's beneficial. And then I think obviously there is, I guess we have never measured this, a lower bound on some, like what's the lowest quality that you can actually do something with. And yes, I mean, potentially like gross errors, like, if your data is so bad that you have bounding boxes overlapping each other, then you could be teaching an ML model that it's okay to collide with other agents, and that like you wouldn't want things like that. So yeah, there is probably a lower bound. It's actually, I think, not something we have explored, but could be interesting.
Right on that point of the collisions, do you guys have any kind of filtering to guarantee that your model doesn't learn that? Because with these data-driven approaches, sometimes it's easy for the models to catch those spurious correlations that you guys were mentioning. So I was just curious if you have any kind of filtering on the data just to guarantee that some behaviors that are exact, you don't really want the model to learn.
Yeah, I think our pipeline does have a few guarantees and some filters on, like, like noticeably, like this is bad data for some reason. I think ideally we'll also kind of like detect those and use those to then improve potentially the upstream, if we are able to. Like some of this fleet data is like offline perception, because you can actually, even though it's lower quality sensor, you can run perception offline. So you can have different models. You can even have models that see what happened in the future to improve the perception at the current time. So when you're looking at that, you can also even go and improve those algorithms based on the filtering. But yeah, we have some filters. I'm not sure we're allowed to disclose.
Yeah, sorry, I didn't want to push that too much. I was just curious. Okay, cool, thanks.
Yeah, one thing I want to comment about that as well is that, like we see that, today in the machine learning community, it's very common, like to only evaluate things on average metrics, average everything, right? So this is kind of one big problem that we see on evaluation today as well, because it was recently shown, if you look, like, for instance, when you train on ImageNet and you do a lot of data augmentation to get performance boost in computer vision, you can see that when you evaluate on subgroups, you are making, you are getting benefits and making an average metric being better at the expense of minority groups, and sometimes you're getting worse in some scenarios. And in self-driving, this is very important. You don't want to miss the tail of the distribution, right? So I would say that, you have to be very careful with evaluation, and the evaluation that we do is very different than what is usually done for machine learning, traditional machine learning models and supervised learning.
It's a good comment, yeah, and often mislooked. Yeah, just to wrap up, maybe we can just ask another question. One that might be on the head of everyone watching this is, what happens if one of the sensors goes down during the inference stage or deployment, and how does a pre-trained model behave in this case?
Yeah, I think I can start taking that. So we cannot disclose much, but basically there's multiple things that you can do on that, right? First is that, well, you can have, it depends of course on the set of sensors, right? So, but the composition of the set of sensors that might go down or up, and what, tolerances you have for that, and how robust your model is. You have all those relationships to think about. But you need to think as well that there is, systems on top of that, right? That are, like the hybrid planner that Anna mentioned, that have safety guarantees that will guarantee that, you're not supposed to have a catastrophic failure if one system goes down, one component goes down, right? So I don't know, Anna, if you want to chime in as well, but yeah.
Yeah, I think it's around that also a little bit about the design domain. kind of like, I mean, that is a work with the product team is, do we want the ML model to handle these situations, or we have some other part of the stack, some other pipeline that handles these kind of like emergency maneuvers. I mean, you could think of it as an emergency maneuver. But yeah, as Christian said, I think it depends on how severe this fault is. Because we could even consider, I don't know if Christian mentioned, but train the model also with like, yeah, what would happen if some of these sensor modalities are down, and like use that in our training data set as well.
Cool, thank you so much. And to close our round of question and answering, we have a question from Andre. What about end-to-end learning methods like the ones Wavi and Wave are pursuing?
Yeah, I can start talking about that. So basically, I cannot talk about Wabi and Wave because I'm not. I don't think they ever disclosure what they are actually doing. So yeah, but like one thing that like we are not still, like I don't think that it is clear that end-to-end learning is the way to go. Like there's multiple reasons for that. One is that, well, the first one is that, well, you are exposing your model to much higher dimensionality data, right? You're going directly from the raw space to decisions, and that that might be, like first thing is that, well, that might be sample inefficient at first time, so you need to have a lot of like a different mechanism to improve sample efficiency, and that's why like if you see like models on end-to-end learning, you have like a lot of auxiliary tasks on that as well. So it can be very tricky, like, but the main problem of that is that imagine that you have to validate those models in virtual validation, right? So, but your model, your policy goes from raw space to the decision space already, right? So how would you do simulation on that? You will need to, like most of the time, you will need to either simulate raw sensors, which can be very difficult. So you end up losing a lot of benefits. And it seems to me that the main benefit of doing that is mainly simplifying the pipeline. So it is not clear. Well, you have, like you increase the, like the observability of your model for sure, because you have access to the entire, like a set of sensors. But at the end of the day, how much of that do you need, right? How much of that do you really need to add that? And why would you expose, like the policy to much more spurious correlations, right? The model would be much easily pick spurious correlations than if you, like kind of only feed information that you need to take decisions, right? So this is something to think about. Is like it's an unsolved problem, and I think there is no clear no clear grounds on that nowadays. I don't think that there is a common sense on that, like what would be better or not. What we see is that there are good things about it, and there are pros and cons. And it seems that at this moment, the cons seems to be a little bit higher than the pros of doing that. Yeah. But it's, like, of course, it's something that we experiment with, and it's something that is quite interesting. Although it, like, it poses a lot of challenges in terms, especially about the doing virtual validation. Yeah. And feel free to chime in as well.
Okay. Oops, sorry. That's all right. Yeah. Okay, guys, thank you so much. We are now officially closing the question and answering section. Thank you so much again for joining us. I will, for the people watching this, I just want to recap that 2 weeks from now, we are going to have another exciting meetup on multimodal AI. We'll have Ricardo Souza from Farfetch telling us a bit about what he's been doing on Farfetch. And also about the session from today, the videos and the slides will be available on the deep learning sessions GitHub that you can check later on. And also don't forget to fill in the feedback form, give us some ideas for future talks that you would like to have us hosting here. And if you also have something interesting that you would like to share, feel free to send us an email or contact us. And yeah, thanks again for your participation and for you at home attending this meetup, and hope to see you again soon.
Thanks a lot, everyone, for attendance and the questions. So it was very interesting.
Thank you.